Good evening, class. Let's start our today's lecture. So, some announcements first. Today we will discuss about the Gauss law and the potential, electric field and potential. And we will quickly try to cover these topics. And for the rest of the lecture, we will try to revise our previous course and some tutorials. And probably I will solve one sample midterm question. So you can have an idea about the mid. So I have two sample papers for you. Uh, One we will discuss during the class, and another I will upload to the portal. Okay. So and later on the solutions for both. So for the midterm, next week we will conduct our midterm test, and most around the course that we have discussed and covered during the class. Okay, so you can expect similar questions or similar type of questions. Okay, let's start with first topic, that is the Gauss law. Uh, Let me revise some important concept before we did. So Gauss law is a very beautiful statement that tells us about what's the connection between the flux lines and charge. We have learned in our previous discussions that if we have a charge, like any uh, conductor, any object, any metal that has some charge inside it, or is charged through some external source, and if it develops some charge, uh, it must have some electric field. Okay, so electric field means that if you bring another charged particle within this field, either it will attract or repel each other. Okay. Electric field also has some beautiful properties, right? One is repulsion. Another thing is that the electric field is uh, or plane conductor. Electric will be directly perpendicular to the surface. If it is spherical, and for every spherical patch, it's again perpendicular. And as you move up, the electric field line become more weaker and weaker, right? So they actually have an angle between and another thing in our last chapter is what's the electric field of infinite of charge. The electric field is equal to the charge divided by epsilon naught, and that means that the electric field is constant with respect to the if the sheet is quite large, right? And you can experience a constant electric field even if you move a little bit away from the surface. Another important thing we learned: electric field never cross each other. Okay, I'll explain. So electric field line, they never cross. The components of electric field will cancel each other. The final or resultant electric field will be again some of the previous two lines. Okay, so these are the some important properties of electric field. Now, electric field can give us the field lines, or what we call the number of field lines, or what we call electric flux, right? So now this is quite straightforward. This is the source. Source produces field, and of course, more source, the field line, electric field, and the more we have, right? Now, this is very clear, but what is the relationship between flux lines and the charge? That's what we call the Gauss law. So Gauss law will tell us what is the charge and what is the electric flux and what is their relationship. Uh, if you look at the book and the notes, the questions are quite complex, right? I will try to make them more simpler. Okay, so that's why I have write down these short equations. If you look at on the top, you would see that the electric flux phi e is actually equal to E dot ds. So this is the same derivation that we have done in the divergence part, right? That means that for every surface, right? So the E vector dot product with the patch area A, right? And then you sum up all this, you will get the total flux, right? Remember, we did some experiment or tutorial problem to find out the total flux from the 6 sides of the cube, right? So the flux actually is the surface integration of E and the area. Okay. Now, if you know the surface, right, then you don't need to do integration, right? For example, if it is sphere, right, then electric field times the perpendicular patch, that is the area, is give you the flux, right? So we know that the area E dot ds is actually equal to 4 pi r square for sphere. If you have a sphere, the area is 4 pi r square. Okay. Now put that one here and you will get the flux equals to E times 4 pi r square. Okay. Okay. Now we also know from the Coulomb's law that electric field is equal to Q over 4 pi epsilon naught r square, right? Put this value into this equation and then you will get this formula. Flux is equal to Q over 4 pi epsilon naught r square times 4 pi r square, right? So this thing and this thing cancels out and you will find a relationship between flux and charge. Okay. Now, flux is equal to Q over epsilon naught. Now, what does this physically means? This means that the more Coulomb charge you have, the more flux lines you have. But there's epsilon naught, that the permittivity of the free space, right? So that means that the charge multiplied by 1 over epsilon naught will give you the electric field lines, right? Or the flux. Now we have completed this part here. Q gives electric field lines and flux using the Gauss law. Now, this is also important in understanding the Gaussian surface, because you know that the circle on the integral, when we are doing the tutorial about the divergence, we learned that it must be a closed surface. That's how that's how we can apply the closed surface integral. That means that the surface should be closed. It doesn't matter whether it's a sphere, it's irregular, but it should be closed. There shouldn't be any holes inside. So the charge, when you put a charge inside the sphere or to charge the whole sphere, it develops charge on the surface of the sphere, right? So there shouldn't be any electric field or any flux line inside the sphere, right? Rather than the charge will be on the surface of the sphere. So if you have done this, then we move to a very important part of the Gauss law. Okay, so far it's right. The flux is actually equal to Q or epsilon naught. Right? Flux is also equal to E dot ds. Right now, look at some other equation here. Because because E dot ds is equal to flux, right? So we can change E into D. So D is equal to epsilon E, right? So we can put D, we can have Q here. Q, and we can have. So that means that D or epsilon naught, this epsilon naught here is equal to this one cancel out, and we can find D dot ds is actually Q, right? So that means that if you know the flux density, right? If you know the flux density, then you can integrate it over the surface area and you will get actually the flux, right? Or you can have a charge here, right? So that means the charge is responsible for producing the flux lines. Okay. Now, if you recall the divergence theorem, right? Now we are trying to sum up all the quantities in one picture. So, do you remember the divergence theorem? Can you go back to your notes and help me to write the divergence theorem? The divergence theorem says that surface integration of some quantity is actually equals to volume integration of that quantity, but it should be in the form of a divergence, right? Correct? It's true, right? That's the divergence theorem. So the divergence theorem tell us that for the surface integration, for surface integration, can move volume integration or replace the vector field with the divergence. That's how we move from surface to volume or volume to surface. Remember the tutorial problem we did in our last lecture. Now, can I put d dot ds equals to q for this one, right? So from the above derivation, I know q is equal to this one. Okay. So that means that q is also equals to this one, right? Correct? Please take some time to understand. So q is equal to this one, already know, and this is the divergence theorem. That means that this and this is also equal. Okay. Can you tell me what does this means now? So for what quantity, if we take the volume integration, we get the charge? Yes, charge density. So if we have a charge density, we take the volume integration, we get the charge, right? So now I can write here as a, so this is the Gauss law. This is what we call the differential form of a Gauss law. And this is what we call the integral form of a Gauss law. Okay. Actually, both are the same thing. Right? But now you would also understand this is also the Maxwell's first equation. Okay. So let's look at the picture again. So you have a charge, no matter how you charge it. Maybe you can take a metal and rub it with the cloth and plug it into the sphere, right? So the sphere gets charged. Okay. Now, if you cut the sphere, right, and you place some scope inside the sphere, you would feel that it can sense the electric field, right? But if you close the sphere, right, make it a closed surface, then you will see that inside there's no electric field. All the field is outside it, right? That's what we call E dot ds, right? So E dot ds means that you have a sphere and all the flux is emanating from the sphere surface. And the electric field is going outside. Now let me show you some properties. What I mean to say is, if you have a sphere like this and you place a scope here to sense the electric field, right? And if you put some charge here, this will show you some deflection. right? But if you have a complete sphere, that's a Gaussian surface, right? Now there is no deflection, right? Because all the electric field is now on the surface of the sphere. So in mathematics, we write this as a E, and this part, the patch, is our dA. Okay, so now this E dot ds is our flux, or the D dot ds is actually equal to charge. Correct? That's the physical meaning, right? So what does it mean? It means that for every surface, let's say if your surface is flat, right, and it develops some line charge density, okay, then there is some line unit here. That should be your E, right? So this E dot dl, that means perpendicular to the plane, right? So if it is a sheet, right, so all the field lines will go up, right, and down. Remember, we learned the electric field is plus minus z rho s over 2 epsilon naught. In the last lecture we learned. So electric field is always perpendicular to the surface. Now if the surface is curved, right, then every curved surface has a small differential area dA. So this dA is in this direction, and electric field is also in this direction, right? So you take the dot product, E times area dot cos theta or cos 0, which is 1. That's how you will get the electric flux. Or if you have a D, you know the epsilon naught, the uh, E epsilon naught of air or medium, then you can directly find out the charge. Okay. So now we have completed the cycle, that is charge produces electric field and electric field produces flux, and flux produces links with charge. Okay, that's called the Gauss law. Okay, now going back to the previous discussion. So we will always have two forms, or we always have two shapes to describe the quantities, right? One is very simple in terms of integral, right? You know, integral means summation, right? So we have summation of d dot ds that tells us the q. Lot of d dot ds, and then you add them together, you get a charge. But we also have a counter form, which is in the differential form. That's what the Maxwell equation says. Now you can understand the importance of the operator divergence. So if you have the charge density, that tells you how much charge is spread over the surface, right? Because the charge is responsible for the flux density, right? D. Then you take the divergence and you will get the charge density. If you know the D, then you can take the divergence. It will tell you the rho v, and rho v is a scalar value. It will tell you the amount of flux that actually for this specific area corresponds to, right? Whether the flux is going out, going in, or remains constant, right? So these two forms are known as the Gauss law. Now we will have a similar discussion here, okay? But for this slide, there is no proof, right? So I suggest you use the previous two slides as a derivation, right? So we have all the derivations from the right from the Coulomb's law, right from the flux, and then you can prove it very easily. There are many other ways also to prove it, but this is more simple way to understand this, right? So you can understand from the first equation, which is the differential form of Gauss law, we have derived now. Divergence of D will give you the charge density. And then if you take the volume integration on both sides, you will get the charge, right? That's also the integral form of the charge, okay? There could be many applications, right? So you can apply this to find out electric field of some special cases. For example, if you have a long wire, right, that has some charge density in the then it's placed in the free space, then what is the electric field, right? Now we can use this equation. Charge is equal to d dot ds, right? Now, charge is equal to rho L times H, line density, right? Because line density is charge per unit length. And if you multiply with the length, you will get the charge. So solve this integral for this shape. Remember, this is a cylinder, right? For cylinder, ds is r d phi dz. Okay, you look at here. So we learned that the the charge or the flux is that's coming from this charge density or this charge deposition, the area and the d must be perpendicular to the surface. Okay, so we can use the d into two forms. One is the this dr stands for the magnitude value of d, right? And the direction is r here because r dot r is 1, so we only get the magnitude back. So if you integrate from d phi 0 to 2 pi, you will get 2 pi. And if you integrate dz from 0 to h, you will get h, right? Or you can directly write 2 pi h. That's the total circumference. So you can cancel h and h here, and you can find out the rho L, right? Now, how to find out the electric field, right? So electric field, we know that D is equal to epsilon naught E. So E is equal to D over epsilon naught, right? So put the value of D from this equation to this equation, and you can easily find out the value of E. Now, this is the electric field of a line charge density. So if you know the charge density of a conductor, right, you can compute the electric field, right? Now, more important thing, what is the direction of electric field? That is radially outward. That means if you have a conductor, right, that is in the form of a line, then electric field will be just like the outside in the radial direction, r direction. So this would be E. That should be the E from all the sides because it's along the r direction. Okay. Now we will try to find out what is the relationship of all those uh, stories and all those theories to the voltage, right? So you should also think about the connection between previous topics. Learned about charge, we learned about electric field, we learned about the force because the Coulomb force tell us how two charges can interact with each other. Electric field tell us that how a charge can produce electric field. E is equal to Q over 4 pi epsilon naught R square, right? Gauss law tells us what's the relation of D, charge density, and the charge, right? And then we can use these formulas to compute the electric field of a sheet or electric field of a line. Now the story is, what about the voltage, right? If we know charge, can we find out voltage? Or if we know electric field, can we find voltage? That's what we are doing right now. Now I'll begin with some classical definition of voltage that you have learned in the school. So this E vector represents the electric field. Of course, the source is charge, right? If you have a charge, then it will produce electric field. Now, the definition of scalar potential, remember it's a scalar potential. That means that the potential or voltage or the scalar potential or potential difference, it's just a scalar value, right? It does not have any direction. So in order to find a potential, we should assume some charge that we have to move it against the electric field, right? So such that the work done on that charge is equal to 1 volt. So definition is if you move 1 coulomb charge against the electric field to 1 meter, that's your 1 volt. Okay. Now, based on simple phenomena, we again use the vector calculus and we do this in the form of in the form of work done. So external force is equals to minus Fe, right, which is actually equal to Q times E. Remember, this comes from the Coulomb's law, right? Force on a charge is equal to QE. We did it in the last lecture. Force is equal to QE. Because it's on the opposite side, that's why we use minus sign. How about the work done? So work done is equal to force time distance, right? So we have QED. Okay. Now, what is the direction of E? E is moving into minus Y direction, right? And the DL is moving along Y direction. So Y dot Y is 1, minus minus is plus. So the work done is QEDY, right? Uh, so you know that the work done is similar to potential, right? The unit of work done and potential are same. If you move some object into a linearly on the Earth's surface, right, from point A to point B, right, you can have a work done. But if you pick up something against the gravity, that's called the potential energy, right? MGH, right? Same, exactly same thing we are doing. So that's the work done, that's the energy, that's the potential, right? So we call it electric potential. That means that just try to imagine we have now, if you lift something, right? So you move it against some force. What is the force? Gravity. Right? So you move something against the gravity and you put it on a height. That means that energy is stored in the object, right? Whenever you move it, it will fall down. That has stored the energy, right? Same thing happens to the potential. So you move your charges against the electric field and put them into some higher position, such that when you connect the load, they go back again to the same potential, releasing the same amount. Right? That's what we call the voltage. So the same principle. If you move the subject object against the earth earth magnetic field, that's called the potential energy, right? Now we are moving charges against the electric field, right? Because the charges, they want to move away or they want to move along the side of electric field, because we learned that the electric field is due to the charges, and you place another charge within a charge, of course, they will repel. Or so that means you have to do some work them into a higher position, right? So that's exactly what you do in your battery, right? So you supply external field and you move charges to a certain plate, anode, and then the difference between, so the energy is actually stored in form of some chemical process, right? And if you remember the application, we learned in the first chapter about the solar cells, the the process when a photon hits the solar cell, right? So it releases an electron, right? And then it's captured through a p-n junction device, right? That's moved to a higher value. So now we have a work done, which is QEDY. This is the energy, okay? So we call it differential electric potential, okay? Call it differential electric potential, okay? Now make this make this energy make this work done aligned with the voltage. So how to convert work done into voltage, right? Work done per unit charge. Work done per unit charge is voltage. Now divide this by the Q and you'll get E dot dl, right? You get E dot dl, right? So what is this dot dl means? Distance. That's it. Line integral. Okay. Uh, what's the unit? Joule per coulomb or voltage, right? That means electric field has a unit of volt per meter, correct? Right? Volt per meter. In our first lecture, we saw from Coulomb's law, from the top, the unit is Newton per coulomb. It's same as volt per meter, right? Now you can see that actually it's the same story. This electric field, electric field, charge density, right? Moving into the air, epsilon naught, correct? And then within some distance d have voltage, right? Moving closer, different voltage. Moving far away, different voltage, right? Depends upon the app, right? So the main source is charge. Charges have electric field, right? So electric field is something that can produce. Now, if you connect, voltage will produce a current, right? Same story. Let's look at how we are actually converging toward more classical definitions of voltage and current in electric circuits. Okay. Now you see, can you see these blue lines? These are electric field. Okay. So we have electric field now. What I'm trying to do is I'm moving in a path P, sorry, point P to P2 by using path 1, path 2, and path 3. Okay. So what are your expectations? So if I cover or if I travel on C1, C2, or C3, will I have the same potential or different? Same, same or different? Difference? Why? Yes. Any other point? Yes, distance is not same, but distance covered inside the electric field is same. So let me tell you why. This is very beautiful representation. So I have one object, okay? Okay, I pick up from the floor, right, and put it here, and then put it here. Okay, that's the one path. Another path, I directly take it here. Same energy, right? So you move from one floor, second to third, third to four, four to second, second to 10. It's same as from 0 to 10. The energy remains the same, potential energy, because mgh, height is same. No? So you walk from level 1 to 4, then go back, and then come again. Maybe move to another floor, then go to the top, or you directly go from 0 to top. The height remains same, mgh remains same, right? Technique that, because this is a line integral, right? Right, and you are working for E, right? So as long as this E is same, right? It doesn't matter you use this path, or this path. This integral remains the same, right? Because point P1, the reference points, and P2, the coordinates, they are same. E is same, right? So your starting journey and end journey, they finish at the same point. Now this is what we call the integral form. I give you more practical example. So you have a circuit, right? Right. So you have a parallel circuit. You have one resistance, and then you have two more resistance on a parallel path. Right. Right. So if you solve these circuits, right, you would see that So this V1 on C1 and C2 remains same. So it doesn't matter which path you choose, as long as they are within the same potential points, right? The voltage is same. The same applies here. Same applies here. As long as these points are same within the electric field, right? They're same. The voltage is same. So that means that if you have a longer wire, if you have a shorter wire, right? As long as they are along the same potential difference, the value is same. Okay. So we learned that the potential that's called the dV between point P1 and P2 is equal to negative of E dot dl from P1 to P2 and independent of the path. Okay. In more real world scenario, we can write dV in the form of a V21, right? What we call a potential difference is equal to V2 minus V1 is equal to negative P1 P2 E dot dl. Now, what does this formula tells you? If you know the electric field vector and you know the points P1 to P2. So what are these points? These are coordinates. If you know the coordinates, right? So what the coordinates do? They'll give you the length, right? If you know the coordinates, you know the electric field, you can find out voltage. And for a closed path, right? So can anybody explain me what does this mean? Why this is zero? E dot dl is zero. Sorry, closed circuit. Yeah, that means that the voltage rise and voltage drop, if you sum up, it's zero, right? Right. For example, if I have a circuit here, right? So if I'm giving 12 volt here, right? So 12 volt will be here. Or if you have a V1 plus V2 equals to V, right? So one is positive V and another is negative V. Or mathematically we write like this, right? Sum of all the potentials is zero. So that's exactly the same meaning. So that means that if you choose a closed path, again to the same point, irrespective of the path, right? Then you have minus 5. So 5 minus 5 is 0. Right? So if you have electric field, then you move away, you will get a lower voltage. Now, so what does it physically means? You should understand that, let's say, if you have some charges here, right? Then you have electric field here, right? Remember, this should be perpendicular. Okay. So sometimes we call it equipotential surfaces. Remember, I told you equipotential surfaces, right? So that means that now that means that if you move from here, right, electric field decreases, right? So how it decreases? 1 q over 4 pi not r square. It decreases with the square of the distance, right? If you are here, maybe there's no effect, right? So if you move away, right, you will find E decreases. So does the voltage, right? So the voltage at here and here are different. But within a certain proximity, there is a region, what we call equipotential. That means that within this region, the voltages are same, right? Say here, 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 all these volts within this region is same. Why it's same? Because E dot dl is same. same distance, same electric field, right? Because electric field is symmetrical from all the surfaces, right? That means E dot dl is same. That's exactly what happens when you have a a earth earth terminal with some potential, right? Let's say you have a short circuit, right? And then you see that the earth acts like a medium, right? And when the electric field goes again and again forward and the backward, it creates equipotential surfaces, right? So you assume there's a live conductor here, right? Positive charge, right? And this is your, let's say the earth is uniform, right? The soil inside is the moisture is uniform. Therefore, the electric field is quite uniform, right? Then you would see that near to this live conductor, right? You would see that there's a high potential here, and you move away, 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 the potential decreases, right? Because the distance increases. Okay, so if you place your 1 foot here and 1 foot here on two equally distant points, equidistant potential, then you won't feel any potential difference. You won't feel any shock, right? As long as you step here and here, right? So you have V1 and V2 between your legs, right? Then you can feel a shock, right? So you have to move within a region where the potential is same. So you don't feel V2 minus V1, right? So we can see that the potential is also a function of distance, right? So as the distance increases, potential decreases. Okay. So mathematically, if you know the E field vector, if you know the points, you can easily find out the voltage, and we can prove it by some formula or the tutorial I will explain later. Now, here are some important formulas. This formula you should remember. Okay, we can ask you some question in the midterm. I'll give you some sample. Okay, uh, this is potential difference because we have two voltages, right? Let's say 10 minus 5 volt. This is simple potential. Can anybody tell me why we have a infinity sign here? What does it mean? It means one point is infinity. What does it mean? Is that if you have a source, right, and one point is inside the electric field, another point is very, that's what we call ground, right? What does it physically mean? It means ground terminal, ground. So what is the potential? Neutral, right? It's very, very far. So the potential is 1 over infinity 0, right? So what does it mean? It means that if you want to evaluate a potential of a point, then you have to take the difference, because integral has two limits, right? So you always have to use the 2 points. So if you want to evaluate a potential of voltage of a single point, then you might consider another point infinity. That means out of the electric field. If one point is out of the electric field, that means it's infinite. The distance is very large as compared to the electric field. That means the potential at that zero, called ground, V1 minus 0, right? So that's the potential. You will get volt. That's the potential difference. Now, this is how electric field and voltage can be linked together. But we already know the relationship of electric field and charge. Okay, so that's electric field. Put electric field in the formula, and you will get a relationship between charge and voltage. Why earth is not? You mean I should put 0 here? That's what you mean? Yeah, okay, I'm telling you. Not this point means doesn't mean voltage. This point means position. Okay, so you have a good question. Let me explain to you. So this is charge, right? This is the charge. So if I am here, right, P2, P2 here, P1 here, right? So electric field cannot reach here, right? It's very far, right? Right? So what's the value of electric field here? 0. Yeah, yes. Here electric field is 0, right? Yes. So the voltage is 0. Now here, what's the voltage? V1, right? So what's the difference? V1 minus 0. So the ground has a 0 voltage. So if you move your point away from the electric field, then you will get 0 voltage. That's what we call the ground voltage. Ground has ideally 0 voltage. That means there's no electric field inside the ground. Yeah. Maybe 20 meters away from the electric field. So 20 meters from electric field means almost infinity. Now, so here, now you can also prove the concept from this formula. So voltage equals to Q over 4 pi epsilon R. That means that voltage is a function of a charge and distance. It means that if you move away from the charge, right, the voltage decreases. Right? If this R is infinity, what is the voltage? 1 over infinity is 0. Right? That means that if you are far away from the charge, you will get 0 voltage. Now, this is also very important formula because it gives you the relationship between charge and voltage. This is also important. This tells you voltage and charge, and this tells you voltage and electric field. Okay. So in exam, we can ask you these type of questions. We can give you electric field and ask you find the voltage. We can give you charge. We can ask you to find the voltage. Okay. Now we know what is the relationship between charge and charge density. Now use the 3 formulas of charge density. You can put it here. And you can modify the formula with respect to charge now, right? So remember Q, the charge density, the surface, Q is equal to rho S ds, Q is equal to rho V dV, and Q is equal to rho L dL. Just replace this and you will get, for volume charge, you can find out voltage. For surface charge, you can find out voltage. And for line charge, you can find out voltage. Okay. Let's move to another important thing. Remember in our derivation of gradient, dt was equal to del or dl, right? Does anybody remember that formula? When we looked at the scalar fields, we found out that dv dt is equal to d del t dot dl. That's uh, the gradient, right? Correct. We learned from our previous chapter of the gradient. We learned from the directional derivative. At that time, the formula was like this: del t is equal to, sorry, right? So we learned about this. Okay. Now, if this is true and dv is equal to e dot dl, right? Then if you compare these two, dv, dv, d, that means that that v now equal to e, right? This is again very interesting. That's the reverse relationship between voltage and electric field. If you know the electric field, right, you take the function, you do the line integral, you'll get the voltage, right? But if you know the voltage, you take the negative gradient and you'll get the electric field. Okay. So now let me show you again. This is scalar field, right? So gradient of a scalar field is vector field, right? So now imagine you have a charge that has electric field, and when you move away, right, the voltage changes, right? So you take the gradient of voltage. That means it tells you the quantity where it changes and in which direction it changes, right? So that's your E, right? So that's the pure representation of how a scalar field and vector field can be combined into the gradient function. This is your scalar field, and this is your vector field, right? So both are linked either in integral form or in differential form. You take the integration of voltage, take the integration of electric field, get voltage. Take the derivation of the voltage, you get the electric field. Negative sign indicates that just invert the vectors. That's it. So sometimes we ask in exam, V and E, how V and E are linked together. Okay. Now the first question, determine the electric potential at, oh, sorry. Okay. Okay. Okay, let's solve the tutorial problem. So negative means you change the vector size. If they are going down, move them up. That's it. Okay. So now let's start the real business now. Okay. That was the discussion, and now we will. This is important question we have asked before in midterm. So the I would request you, or maybe suggest you, when you are making the preparation for your midterm or final exams, you should always prepare one sheet, right, for your reference, for your understanding, so that you can understand everything on the fingertips. So this question is asking about determine the potential due to four charges, right? So that means we are now discussing the potential. That means voltage, scalar field, versus charges, right? So there should be some formula. If given charges, how to find out voltage? That's it. Now this question is asking you to find out the voltage. If you are given four charges, 20 microcoulomb in a 2 meter by 2 meter square, and the voltage is at this point. Okay. Remember, one charge can produce electric field, and then if you move away from charge, you will get some voltage. If there are four charges, they will interact each other, right? So we can directly write down the voltage formula. V is equal to 4 times Q, right? If you find out the voltage due to 1, voltage 2, voltage 3, voltage 4, just add them together. There's no need for vector calculus because voltage is a scalar quantity, right? Voltage does not have any unit vector, right? So just solve it simply just adding the four values. So that means that the charge, because it's 2 meter by 2 meter, right? And the charge is at the point is at the center. That means that this value is 1 and this value is 1. So what's the distance? So the trick in this question is that you are not given the distance between charge and the point of finding the voltage. So the geometry will tell you the distance. Okay. So what is R? So we know that R is equal to, by using the Pythagoras theorem, 1 square plus 1 square is equal to R square. And R is equal to 1 square plus 1 square under root 2, which is under root 2 meter. Okay. So R is given. Now plug the formula. So we know the formula for voltage is Q over 4 pi epsilon naught R. This is voltage due to one charge. If you have a 2 charge, 3 charge, 4 charge, add them together because it's a scalar quantity. Okay. So instead of 1Q, now you use 4Q because there are 4 charges and they're equal. Okay. So 20, remember this micro, so we use 10 raised by minus 6. We use 4 pi epsilon naught R, and the answer is in the volt. That's it. If you can solve it, you can get 10 marks easily. Anyone who finds it difficult? So what I'm trying to say is, when you prepare for every topic, just give it a very short name. Given a key or given a charge or primary voltage, right? And let's go through all those relationships and put them into mind. So you have a very good graph for all the fundamentals. I think it shouldn't be any problem by this point. The only thing that confuses you is that a baby charge, density, voltage, and all those will get mixed up. So make sure you have the proper formula for each of the three and apply this. This question is about given a charge, how to find a voltage. Next question is given electric field, how to find the voltage. Okay, let's do it. It's done. It's clear. Okay, let's. So can you solve it by yourself? Given an electric field, okay, E is 6x square. I can write it even. You can also understand the quantity by looking at the unit. The unit of E is volt per meter. So find Mn. That means that, of course, these lines are not straight because it depends on the E, right? So there is one point M and there is another point N. Find out the voltage Vm. If you are given M, you are given N, you are given Q. Find out the value of voltage Vm. N is, first solve this one and then solve this one. So E is given, M is given, N is given. Find out the voltage Vmn. You can use the formula of integral Vmn equals to minus E dot dl Nm. Please try this, then I will help you. Find out the formula of electric field and voltage. Okay. So that's how you can solve E dot dx. So E is given, right? Because E has X, Y, and Z components. Okay? And these are the length components, X, Y, Z, X, Y, and Z. You can also make it three integral. Take the X limit, dx, Y limit, dy, Z limit, dz. Or you can do like this. For example, dx, you can take X, dy, Y, and Z. Here I solve the x dot x is 1, 6x integration is 6x by 3. That's why we have this one. Y dot y is 1, 6y has 6y squared by 2. That's why we have this one. So when you're using the x limit, only use 2 and minus 3. Using y, 6 and minus 3. Z minus 1 and 8. If you are not familiar with this, then you can also use like this. Minus E dot dl, use x limits, right? Or minus E dot dl, use y limits, plus minus E dot dl, use z limits, right? You can also separate three integrals, it's same. For the B part, Vm, if voltage is 0 at Q, then that means that voltage at Q is equal to 0. So the trick here is first you find out MQ. Okay. So you find V and Q. Next question is, third part is find Vn if voltage is 2 at P point 1, 2, minus 4. Now, because 2 points are given, we can find V and P. Vn is equal to Vn. V is equal to 2 means that Vp equals to 2. So once you evaluate the integral, you don't need to do it all the time. Okay, just take the integration one time and then use it for rest of the questions. Fine. Okay. Okay, let's take a 5 minutes break. Okay, I'm here to answer your questions. Please come back and then all the practice. Voltage is zero at Q. That means dq is zero. So that's why this is zero.